All right, so we are going to go through the example of 3.60. So I'll just read it for you. A spherical tank of 4 meters diameter contains a liquefied petroleum gas at negative 60 degrees Celsius. Insulation with a thermal conductivity of 0.06 watts per meter Kelvin and a thickness of 250 millimeters is applied to the tank to reduce the heat gain. So first A, determine the radial position in the insulation layer at which the temperature is 0 degrees Celsius. When the ambient air temperature is 20 degrees Celsius and the convection coefficient on the outer surface is 6 watts per meter squared Kelvin. And then B, if the insulation is pervious to moisture from the atmospheric air, what conclusions can you reach about the formation of ice in the insulation? What effect will ice formation have on heat gain to the LP gas? How could this situation be avoided? Right, so we're just going to start by going through the givens. So first we have the diameter equals 4 meters. And if you take that, we'll do radius 1 equals 2 meters. We'll assign the radius numbers later in the image. We have Tg, which is temperature of the gas, equals negative 60 degrees Celsius. We have K of the insulation, which equals 0.06 watts per meter Kelvin. And we have the thickness of the insulation, which equals 250 millimeters, which equals 0.25 meters. So we are trying to find a R where T equals 0 degrees Celsius. If the T2, which is going to be the outer radius, equals 20 degrees Celsius with a heat transfer coefficient of 6 watts per meter squared Kelvin. And then B, I'm not going to rewrite it. We're just going to answer that question. So we go through and you kind of just draw this. It's a little over exaggerated, but we have R1. This is R2. And I am just going to call this R. So this is just some random R. Like I said above, R1 is going to equal 2 meters. We'll say R2 equals 2 meters plus that 0.25 meter thickness, which is 2.25 meters. And so T without notation, 0 degrees Celsius. T2 relates to the temperature at R2, and then R1 is obviously that inner temperature. So I'm gonna add another page. We're gonna start with A. So we're gonna start with some thermal resistance. So we have T1, then we have T2. So we have that our conduction, which is also our insulation, and then our convection. So we have the thermal resistance of the insulation. So our insulation equals 1 over R1 over 1 over R2 over 4 pi K, which equals 1 over 2 meters minus 1 over 2.25 meters, which is 4 pi times 0.06 watts per meter Kelvin. We get our insulation equals 0.07368 Kelvin per watt. And then if we go over here, we'll do our convection, which equals 1 over H A. So this is the surface area, which equals 1 over H times 4 pi R2 squared. And then if we plug that all in, you get 6 per meter Kelvin. That's squared times 4 pi times 2.25 meters squared, and that is all over under 1. And then if you do the math, you get 0.002619 Kelvin per watt. That is for the insulation. And if we do go over here, you can find Q equals T2 minus T1 over our insulation plus our convection. Get Q. If we plug everything in, 20 minus negative 60 Kelvin is 0.07368 Kelvin per watt plus 0.002619. Q equals 1048.50 watts. So if you look it up, for a hollow sphere, we know that Q equals 4 pi K T minus T1 over 1 over R1 minus 1 over R. So we've already calculated Q, we have K. We know it was given to us, T equals 0 degrees Celsius. We know T1, we know R1. We will just solve for R. So if you do a bunch of rearranging, you get R equals 1 over R1 minus 4 pi K T minus T1 over Q. And this is all the negative ones. This will be all over, or 1 would be over this. And so you get R equals 1 over 2 meters. Watts per meter Kelvin. Oops. And that is all over that Q we just solved for, -1. We get R equals 2.188 meters. And then, so I'll just zoom out so you guys can take a little look at what this all looks like together. And then just for B, if we're thinking through it, so we get water into this insulation, and then you have the formation of ice. And we all know, just kind of logically thinking through this, when water turns to ice, it expands. So there'd be kind of an expansion of this insulation, which can form cracking, et cetera, which would let more heat into this sphere. So there'd be an increase of heat transfer. The insulation would not be doing its job as well. And how can we avoid this? Install some type of barrier to keep out moisture. So yeah, that's just logically kind of thinking through part B. I'll just kind of zoom out again for this. And that is how you solve 3.60.